Welcome to the Gridcentric demo screencast. In this video we will showcase our automated horizontal scale-out appliance, Reactor. It uses Gridcentric's virtual memory streaming to create new servers on the fly. Reactor presents a UI to handle endpoints or web services. It will gate all requests to the web service and redirect them to an elastically sized server pool. In this example, a service called JMeter is configured with a minimum of 1 and a maximum of 10 servers. For the purposes of demonstration, Reactor will strive to keep the maximum request per server at 8. New servers in the pool are cloned from a snapshot using virtual memory streaming. In order to list the instances in the compute host, we transition to a shell window. The Reactor JMeter instance is itself the scale-out appliance. JMeter server is a live instance from which we will create a snapshot using the bless command. All commands we type on this shell are easily automated via an HTTP RESTful interface, as is common in OpenStack. We obtain the ID of the snapshot that is being created and configure Reactor to use it as the basis for cloning. The process of creating a snapshot may take a while, but once finished we can activate the Reactor managed service. After bootstrapping the service, Reactor will clone the first copy of the snapshot to satisfy the minimum number of instances set at 1. The UI will show us the metrics that Reactor will use as input for scaling, as well as the current size of the server pool. Back to the shell, we see the creation of the first clone has already been scheduled. Each of these cloned instances will be immediately ready to serve requests. They are configured to respond to each query by performing a CPU-intensive computation. The clone is now active and registered with Reactor. The memory footprint of the clone is 1/10 of its nominal size, thanks to the memory streaming technology. We will use a client workload, which will blast the server with multiple requests, simulating a flash crowd effect. The client reports two metrics: response time, which should be kept low, in a blue plot, and throughput, or number of requests per second, which should be kept high, in a black plot. We now fast forward to observe the behavior of the automatically scaled web service. As load increases, Reactor detects an increase in key metrics and commissions new servers. The servers are cloned on demand, occupying a fraction of their nominal memory footprint. The servers are immediately capable of responding to queries, consuming CPU as expected while doing so. The client registers an increase in throughput as the server pool is scaled out. It measures a similar decrease in response time. Reactor's metrics match those of the client. Near the peak, the maximum of 10 servers are commissioned by the Reactor manager. The memory overcommit ratio for the active servers is well over 5:1. After we stop the client workload, Reactor responds to decreasing load by decommissioning active servers. After an interval of time, the servers are actually destroyed, shrinking the pool back to a single server.